Tonight, we are going to follow the light of the sun to the last place it will ever reach. Not the light that is arriving at Earth right now, travelling through 93 million miles of space in 8 minutes. Not the light illuminating the moons of Jupiter, or the faint glow warming the methane clouds of Titan. We're going to follow the light further than that, boundary of the solar system, past the Oort cloud, into the interstellar medium, and then eventually to the very edge of what the sun can ever send its light to, across a universe that is expanding faster than light itself can follow. By the end of tonight, you will understand that the sun's light does not simply fade with distance. It has a hard boundary, a region beyond which no photon the sun will ever emit can arrive, and that boundary is not defined by the distance to the nearest star, or the edge of the galaxy, or the size of the observable universe. It is defined by dark energy, by the accelerating expansion of space, and by the same physics that determines the ultimate fate of everything in the cosmos. Tonight, we also want to understand what happens to the sun itself, because the light the sun is producing right now is not the last light it will ever produce. In roughly 5 billion years, the sun will swell into a red giant, boil the oceans of Earth, and eventually shed its outer layers in a slow planetary nebula before collapsing into a cooling white dwarf. That white dwarf will continue to glow for trillions of years, and the last photons it ever emits will travel outward through an increasingly empty, cold, and dark universe. Before we get started, the story of where those photons end up is one of the stranger destinations in physics. No one expects the edge of the sun's light to be a place you can point to on a map. It is not a line drawn in space. It is a cosmological limit, a consequence of the fact that the universe has been expanding since the Big Bang, is accelerating in that expansion, and will continue to accelerate until the fabric of space-time itself is stretched so thin that no signal from any source can ever cross the distances that have opened between galaxies. The sun is one small fire in a galaxy of 300 billion fires, but its light and the arc of its eventual death can teach us something about the fate of every light in the universe. Tonight, we are going to cover all of it. We will start with the photon itself, the nuclear furnace of the sun's core, and follow it through a journey that takes hundreds of thousands of years just to escape from the interior. We will track sunlight through the solar system, through the heliosphere, through the diffuse outer reaches of the sun's gravitational influence, to the point where its photons become indistinguishable from the background light of the cosmos. We will look at what the sun's death will actually produce, and trace those final photons into a universe that is growing colder and darker with every passing moment. And at the end, we will arrive at an answer to the question that opened tonight's episode. The final place the sun will ever send its light is not a location in space. It is the edge of causality itself. Now, let's begin. The number that sets the stage for everything is 186,282 miles per second. That is the speed of light in a vacuum, and it is the fastest that any photon the sun produces will ever travel. In 8 minutes and 20 seconds at that speed, a photon crosses the 93 million miles between the sun and Earth. In about 43 minutes, it reaches Jupiter. In just over 4 hours, it reaches Neptune. At those distances, sunlight is already faint enough that the sun, seen from Neptune, appears roughly 900 times dimmer than it does from Earth, a point of light perhaps 25 times brighter than the full moon seen from Earth, but no longer capable of warming a planetary surface to liquid water temperatures. Beyond Neptune, the solar system continues. The Kuiper belt, a ring of icy bodies extending from about 30 to 50 astronomical units from the sun, receives sunlight that is 900 to 2,500 times fainter than what reaches Earth. Pluto, orbiting at an average of 39 astronomical units, receives sunlight so faint that the sun appears as a very bright star, far more brilliant than any other star in the sky, but not the incandescent disk that rises every morning on Earth. A square metre of surface at Pluto's distance receives about 1/1500th of the solar energy that a square metre at Earth's orbit receives, enough to faintly illuminate but not enough to heat, and yet sunlight continues. At 100 astronomical units, where the Voyager 1 probe crossed the termination shock of the solar wind in 2004, light from the Sun is still arriving. At 122 astronomical units, where Voyager 1 crossed the heliopause into true interstellar space in 2012, photons from the Sun are still travelling outward, mixed with the diffuse radiation of the wider galaxy, but still present, still measurable. The edge of the solar system, by any meaningful definition, is not where the sunlight stops. It is where the Sun's gravity and solar wind lose dominance to the interstellar medium. But the photons keep going. They keep going through the Oort cloud, which extends to distances perhaps 100,000 astronomical units, nearly 2 light years. They keep going until they are so diluted by the expansion of spherical wavefronts that no detector we have could register them against the noise of the cosmic background. And then they keep going still, invisible and unmeasurable but real, carrying a message that the Sun exists, outward into a universe that is already racing away from them faster than they can follow. The photon that left Earth's surface this morning as part of sunlight began its existence not 8 minutes ago, but somewhere between 10,000 and 170,000 years ago, depending on where in the Sun's core it was born. That number is not a typo. The photon was produced in a nuclear fusion reaction deep in the Sun's core, where hydrogen nuclei fuse under temperatures of approximately 27 million degrees Fahrenheit, releasing energy in the form of gamma rays. And from that moment of creation, the photon began a journey through the interior of the Sun so slow, so convoluted and so strange that the Sun itself had time to drift several full orbits around the centre of the galaxy before the photon finally escaped. The interior of the Sun is not empty space. It is plasma, matter so hot and dense that electrons are stripped from their atoms, and the resulting gas is compressed to densities far greater than anything on Earth's surface. In the core, the density is roughly 150 grams per cubic centimetre, about 150 times the density of water, and about 8 times the density of gold. At those densities, a photon travelling at the speed of light does not move freely. It is absorbed by a charged particle almost immediately, emitted in a random direction, absorbed again, emitted again, absorbed again. The average distance a photon travels before being absorbed and emitted in the core is on the order of a fraction of an inch, about the width of a human hair in some estimates. No one expects that description to translate into an intuitive sense of what it means for light. We tend to think of light as the fastest thing in the universe, the benchmark of speed against which everything else is measured, and in vacuum, it is. But inside the Sun, light is effectively trapped, diffusing outward in a random walk that would embarrass a drunk person navigating a room by bouncing off the walls. The technical term for this region, the inner 2/3 of the Sun by radius, is the radiative zone. It is called that because energy moves through it by radiation, but the radiation is bouncing around so many times that the net outward drift of energy is extraordinarily slow. How slow? The estimates vary depending on how the calculation is done, but the consensus range is that a photon of energy takes somewhere between 10,000 and 170,000 years to make its way from the core to the base of the convection zone, a layer where the plasma becomes hot enough and turbulent enough that it starts to move in physical currents rather than passing energy by radiation. The wide range in the estimate comes from the difficulty of modelling the exact paths of the photons, but even the low end of that estimate, 10,000 years, means that the sunlight hitting your face right now was created in a nuclear reaction that took place before the last ice age ended, before the rise of Mesopotamian civilization, before the invention of writing. By the end of tonight, that fact will come up again when we talk about the Sun's eventual death. But for now, the relevant point is that the photon is moving outward, slowly, through an environment where every instant of its existence is defined by absorption and re-emission. The direction of each emission is essentially random. The net drift outward is a consequence of the temperature gradient. The core is hotter than the outer layers, so there is slightly more energy flowing outward than inward at every point. Very slowly walks the photon toward the surface. No one predicts the photon will survive these bounces unchanged. The original gamma ray that was produced in the fusion reaction is not the same photon that eventually arrives at the surface. Every time a photon is absorbed and emitted, it can be emitted at a slightly different energy. The high-energy gamma rays produced in the core are progressively broken down into lower energy photons through this process, so that by the time the energy reaches the surface, it is largely in the form of visible light and near-infrared radiation, the wavelengths that our eyes evolved to detect and that warm the surface of the Earth. The Sun is effectively converting the violent energy of nuclear fusion into the gentler spectrum of light that makes life on Earth possible, one random bounce at a time. When the photon reaches the base of the convection zone at roughly 70% of the Sun's radius, the character of its journey changes. Here the plasma is hot enough that it becomes unstable to convection, the same process that moves heat through boiling water. Great columns of hot plasma rise toward the surface, carrying their energy upward mechanically, and then cool slightly, sink back down, pick up more heat, and rise again. The convection cells are vast by human standards. The largest ones, called supergranules, are roughly 20,000 miles across, about 2.5 times the diameter of Earth. The convection zone extends through the outer 30% of the Sun's radius, a layer roughly 124,000 miles thick. Through this zone, energy moves faster than in the radiative zone, but still not quickly by cosmic standards. The convective motions take on the order of a week to a month to carry energy from the base of the convection zone to the photosphere, the Sun's visible surface. By the time the energy arrives at the photosphere, it is already roughly 10,000 degrees Fahrenheit on its surface, compared to the 27 million degrees in the core. The photosphere is where the Sun becomes transparent enough that photons can actually escape into space, rather than being absorbed immediately, and this is the surface we see when we look at the Sun through a filter. The photosphere itself is a roiling dynamic layer roughly 300 miles thick. The granulation visible on its surface, if you have ever seen a time-lapse of the Sun's face in a high-resolution solar telescope, shows the tops of the convective cells, bright centers where hot plasma is rising, dark edges where the cooled plasma is sinking back down. Each granule lasts only about 8 to 10 minutes before it dissolves and a new one forms. The surface of the Sun is alive with motion on timescales that are brief by human standards. Above the photosphere, the Sun has two more layers that the photon must pass through before it reaches open space. The first is the chromosphere, a thin layer a few thousand miles thick, visible during total solar eclipses as the reddish ring around the edge of the Sun. The second is the corona, the Sun's outer atmosphere, which extends millions of miles into space and reaches temperatures of several million degrees Fahrenheit, dramatically hotter than the photosphere in a process that is still not fully understood. The corona is where the solar wind originates, the stream of charged particles that flows outward through the solar system and inflates the heliosphere. No one expects leaving the Sun's surface to be the end of the photon's interesting journey. Once a photon escapes the photosphere, it is travelling through a region that is still dense with corona plasma and solar wind particles for the first several solar radii. But it is no longer being stopped and emitted every fraction of an inch. It is now free to travel at its full speed, 186 down to 182 miles per second, and from the moment it escapes the photosphere, it covers the 93 million miles to Earth in approximately 8 minutes and 20 seconds. That 8-minute journey through interplanetary space is the photon's first experience of true freedom in its entire existence. Every moment before this, from its creation in the nuclear reaction in the core to its slow drift through the radiative zone to its convective journey to the surface, it has been trapped, absorbed, emitted, redirected. Now finally, it travels in a straight line, and it has roughly 4.3 years of travel ahead of it before it reaches the nearest star system. Or rather, the first of tonight's stories is what happens when it decides not to stop there at all and instead keeps going. There is something else that escapes the sun in addition to light, and it escapes far faster. Every second, roughly 400 trillion neutrinos stream outward from the sun's core, each created in the nuclear reactions that fuse hydrogen into helium. Neutrinos interact almost not at all with ordinary matter, where a photon of light created in the solar core takes between 10,000 and 170,000 years to escape the radiative zone through a process of repeated absorption and re-emission. A neutrino from the same nuclear reaction escapes the entire sun in approximately 2 seconds, passing through the dense plasma of the core and radiative zone as if it were not there. The neutrinos reach Earth about 8 minutes after leaving the sun, travelling at very nearly the speed of light. When they arrive, they pass through the entire planet as easily as they pass through the sun. About 65 billion solar neutrinos pass through every square centimetre of Earth's surface every second, including the square centimetre of your hand if it happens to be facing the sun. Almost none of them interact with any atom in your hand. They pass through as if you were not there. Detecting solar neutrinos requires enormous detectors filled with extremely pure materials and buried deep underground to shield them from cosmic ray backgrounds. The first successful solar neutrino detector was Ray Davis's experiment at the Home State Gold Mine in South Dakota, operational from 1967 to 2002, which used 100,000 gallons of dry cleaning fluid as the detection medium. When a solar neutrino collides with a chlorine nucleus in the fluid, it can transform the chlorine into radioactive argon, which can be extracted and counted. The experiment detected far fewer neutrinos than solar models predicted, a discrepancy that became known as the solar neutrino problem. The solar neutrino problem persisted for decades. No one expected the sun's nuclear reactions to be producing fewer neutrinos than predicted. The nuclear physics of solar fusion was well established, and the predicted flux was reliable. The resolution turned out not to be in the sun's physics, but in the neutrinos themselves. Neutrinos were found to undergo flavor oscillation, spontaneously changing between 3 types: electron neutrino, muon neutrino, and tau neutrino, as they travel. Davis's experiment was only sensitive to electron neutrinos, the type produced in solar fusion. The missing neutrinos had simply changed flavor in transit. This discovery, confirmed by the Sudbury Neutrino Observatory in Canada in 2001, demonstrated that neutrinos have mass, a result that required revisions to the standard model of particle physics. The physicists responsible, Takaaki Kajita and Arthur MacDonald, received the Nobel Prize in Physics in 2015. Solar neutrinos carry information about the nuclear reactions in the sun's core in a way that light cannot. The light we see leaving the sun's photosphere today was created in the solar interior anywhere between 10,000 and 170,000 years ago. We cannot see directly into the sun using photons, it is too opaque. But neutrinos emerge from the core in real time, carrying a direct snapshot of the nuclear reactions happening right now. Neutrino astronomy of the sun is effectively an X-ray of the solar interior, a live measurement of the fusion reactions that power our star as they occur. Absolutely no one anticipates that solar neutrinos will be as useful to future astronomers as photons for observing distant stars. Neutrino detectors are extraordinarily expensive, require massive shielding, and are only sensitive to the nearest and most energetically prolific sources. But for the sun, solar neutrinos are the deepest look we have into the process that creates the light we follow through the rest of tonight's story. One of the outstanding unsolved problems in solar physics is why the corona, the sun's outer atmosphere, is so extraordinarily hot. The photosphere, the visible surface of the sun, is approximately 10,000 degrees Fahrenheit. if temperature simply decreased with distance from the energy source, as you might expect, the corona should be cooler than the photosphere. Instead, it is dramatically hotter. Coronal temperatures range from 1 million to several million degrees Fahrenheit, with active regions near sunspots reaching 18 to 27 million degrees Fahrenheit. This temperature inversion is called the coronal heating problem, and it has occupied solar physicists for decades. The fundamental issue is thermodynamic. Heat normally flows from hot to cold, so a hot corona surrounding a cooler photosphere seems to violate intuition, if not thermodynamics itself. The resolution lies in the fact that energy is being deposited into the corona by mechanisms that have nothing to do with direct thermal conduction from the photosphere. The heat is being added by work, not by a temperature gradient. The two leading mechanisms are wave heating and nanoflare heating. In wave heating, alpha waves, oscillations in the sun's magnetic field that propagate outward from the photosphere, are dissipated in the corona, depositing their energy as heat. Alpha waves are driven by the turbulent convective motions in the photosphere that are constantly jostling the footpoints of magnetic field lines, sending ripples up the field lines into the corona. The challenge is explaining how those waves, which can carry enormous amounts of energy, dissipate efficiently in the tenuous coronal plasma rather than simply passing through it without interaction. In nanoflare heating proposed by solar physicist Eugene Parker in 1988, the photospheric motions that drive wave heating also constantly stress and braid the coronal magnetic field lines. When adjacent field lines with opposite polarities are brought into contact by this braiding, they undergo magnetic reconnection, a process in which the field lines snap and reconnect in a lower energy configuration, releasing energy as heat and particle acceleration. Parker proposed that this happens continuously throughout the corona, in events too small to detect individually, which he called nanoflares, and that the accumulated heating from trillions of these tiny events per second is sufficient to maintain the corona's temperature. Both mechanisms almost certainly contribute to coronal heating, and the current consensus is that multiple processes operate simultaneously in different coronal environments. The NASA Parker Solar Probe, launched in 2018, has been making the closest ever approach to the Sun, dipping inside the corona and measuring the magnetic field, particle populations and wave activity there directly rather than from a distance. The probe has confirmed the existence of magnetic field reversals called switchbacks close to the Sun, which are consistent with the nanoflare picture of a corona energized by magnetic reconnection. It has also measured alpha wave activity consistent with wave heating models. No one expects the coronal heating problem to be fully resolved by any single mission, but the data from Parker Solar Probe, combined with observations from the ESA Solar Orbiter mission that launched in 2020, is providing the most detailed view of the solar corona ever obtained. The understanding emerging from these missions is that the solar atmosphere is dynamic and three-dimensional in ways that could not be appreciated from Earth-based observations alone. Magnetic field structures thread through the corona at scales of a few tens of miles, and the interaction of those structures drives the heating that makes the corona shine at temperatures that dwarf the visible surface. The corona matters for tonight's story not only because it is the source of the solar wind, the stream of particles that inflates the heliosphere and creates the magnetic environment in which the planets move, but also because it is the last environment a solar photon passes through before it escapes into interplanetary space. The coronal plasma scatters some solar light, creating the pearly white glow visible during total solar eclipses. The X-ray emission from the corona is the most energetic light the Sun regularly produces, and the dynamics of the corona, including solar flares and coronal mass ejections, can temporarily increase the Sun's energy output by significant amounts, sending pulses of high energy radiation and charged particles outward through the solar system. A solar flare is a sudden brightening on the Sun's surface associated with the release of magnetic energy in a localized region. The largest solar flares can release energy equivalent to billions of hydrogen bombs in a matter of minutes, sending intense bursts of X-rays and gamma rays outward at the speed of light, followed by streams of high-energy protons and electrons. The most powerful solar flare ever observed on our Sun in the modern era was the Carrington event of September 1859, a flare so intense that the auroras it produced were visible at tropical latitudes, and telegraph systems across North America and Europe were disrupted, with some telegraph lines carrying induced currents even when disconnected from their power sources. Coronal mass ejections are distinct from flares, although the two often occur together. A coronal mass ejection is the expulsion of a large amount of magnetized plasma from the corona into interplanetary space, a bubble of solar material that can contain billions of tons of charged particles, travelling at speeds from about 250 to 3,000 miles per second. When a coronal mass ejection reaches Earth, it can compress the Earth's magnetosphere and inject energy into the upper atmosphere, causing geomagnetic storms, disrupting satellites, and in extreme cases affecting power grid stability. The photons from a solar flare reach Earth in about 8 minutes from the moment of the flare. The charged particles from the accompanying energetic particle event arrive in tens of minutes to hours, depending on their energy. The bulk of the coronal mass ejection plasma arrives 1 to 3 days later. The cascade of effects illustrates something fundamental about the relationship between the Sun and Earth. We are not simply bathed in steady light. We are embedded in a dynamic magnetic environment that connects us to every energetic event on the Sun's surface, with light arriving first and matter following behind it. Before we get started on the final stage of the Sun's story, it is worth pausing on this. The photons we have been following throughout tonight, travelling outward at 186,282 miles per second, are not the only thing the Sun sends into the solar system. They are accompanied by a constant stream of particles, a magnetic field that threads through the heliosphere, energetic bursts from flares, and the enormous plasma ejections of coronal mass ejections. The light is the fastest and the most constant, but the Sun is not only a lamp, it is an engine, and the light is just the most visible product of that engine's operation. The heliosphere is the Sun's bubble. It is the region of space where the solar wind, that constant outflow of charged particles from the Sun's corona, is strong enough to push back against the interstellar medium, the diffuse gas and magnetic field that fills the space between stars. The heliosphere extends outward in all directions from the Sun, but it is not a perfect sphere. The Sun is moving through the galaxy at roughly 43,000 miles per hour relative to the surrounding interstellar medium, and this motion compresses the heliosphere on the leading side and stretches it into a long tail on the trailing side like the bow wave and wake of a ship. The boundary of the heliosphere is not sharp. There are several distinct boundaries at increasing distances from the Sun. The first is the termination shock, where the solar wind abruptly slows from supersonic to subsonic speeds as it hits the resistance of the interstellar medium. Voyager 1 crossed this boundary in 2004 at a distance of roughly 94 astronomical units from the Sun, about 94 times the Earth-Sun distance. Beyond the termination shock lies the heliosheath, a turbulent transition region where the solar wind is subsonic and mixed with interstellar material. This extends outward to the heliopause, the true boundary of the heliosphere, where the solar wind and interstellar medium reach a pressure equilibrium. Voyager 1 crossed the heliopause in August 2012 at a distance of roughly 122 astronomical units from the Sun. It became the first human-made object to enter interstellar space, and the data it returned from that crossing confirmed a set of properties about the transition region that surprised the scientists who designed the mission. The magnetic field direction changed abruptly at the boundary. The density of energetic particles from the Sun dropped sharply, while the density of cosmic rays from outside the solar system increased. The temperature of the plasma dropped dramatically. Voyager 1 did not just cross a line, it crossed into a fundamentally different physical environment. But the photons from the Sun kept going regardless of what Voyager 1 was measuring. Photons do not interact with the heliopause. They pass through it without noticing. A photon that left the Sun's surface 8 minutes and 20 seconds after 93 million miles takes the same time to reach Earth whether the heliosphere is intact or not. Photons are not charged particles. They are not deflected by magnetic fields except under extreme conditions. They travel in straight lines through interstellar space, carrying the energy of the Sun outward at the universal speed limit into a region of the galaxy where the next significant concentration of matter is more than 4 light years away. The interstellar medium between the Sun and the nearest stars is not empty, but it is about as close to empty as anything in the universe. The average density of the interstellar medium in the Sun's neighbourhood is roughly 1 atom per cubic centimetre. Compare that to the air you're breathing right now, roughly 30 quintillion molecules per cubic centimetre. The interstellar medium is 100 quintillion times less dense than the air in this room. A photon travelling through it encounters essentially no resistance and no absorption. It just goes. The nearest star to the Sun is Proxima Centauri, a red dwarf 4.24 light years away, and sunlight travelling in that direction will arrive there in 4.24 years. But Proxima Centauri is a dim star, and most photons from the Sun are not travelling in its direction. They're travelling in all directions at once, spherically outward, spreading across the surface of an ever-expanding sphere. The intensity of sunlight drops as the inverse square of the distance. Double the distance and the intensity drops to 1/4. Triple the distance and it drops to 1/9. At a distance of 4 light years, sunlight is so diluted that a detector the size of a football field could barely register individual photons from it. At the distance of the nearest galaxy, the Large Magellanic Cloud, 160,000 light years away, the Sun is too faint to be individually resolved by any instrument humanity currently possesses. The photon is still there, still travelling, still carrying information about the Sun's existence, but so diluted by its spherical expansion that it is effectively invisible against the noise of the cosmic background. And here is where the journey of a single photon from the Sun begins to connect to something much larger than the lifetime of a single star. Because not all of the Sun's photons that left the surface today will be able to reach all parts of the universe. The universe is expanding. Space itself is stretching between every galaxy and every other galaxy, and it is stretching at an accelerating rate, driven by a form of energy called dark energy, whose nature we do not yet understand. The consequence of this acceleration is that for any given photon, no matter how fast it travels, there is a finite distance beyond which space is expanding away faster than light can cross it. No one expects that to be an intuitive statement. It sounds like it violates the rule that nothing can travel faster than light. But dark energy does not move matter through space. It expands the fabric of space itself. The rule that nothing moves through space faster than light is not violated when space itself expands. Galaxies that are far enough away from us are receding from us faster than light, because the space between us is growing so fast. They are not moving through space faster than light. They are being carried apart by the expansion of space. The boundary beyond which the expansion of space outpaces the ability of light to cross it is called the cosmic event horizon, and it is located at a distance of approximately 16.5 billion light years from Earth today. Photons emitted by the Sun today, travelling in the direction of a galaxy beyond that horizon, will never reach that galaxy. The distance to the galaxy will grow faster than the photon can close it. The photon will travel for trillions of years, covering an enormous distance in space, and yet the galaxy it is headed toward will always be further away than the photon has travelled. It is a race that can never be won. This is the hard boundary on how far the Sun's light can ever go, not the edge of the observable universe, which at roughly 46 billion light years is larger than the cosmic event horizon, because it includes light from the early universe that reached us before the acceleration began. The limit on where the sun's light can ever arrive in the future is the cosmic event horizon. The sphere around us within which space is expanding slowly enough that a photon emitted today can still, in principle, traverse the distance. But tonight's script is not just about where light goes, it is about what happens to the source of the light. Because the sun is not a permanent fixture, it is approximately 4.6 billion years into a main sequence lifetime of roughly 10 billion years. That means we are slightly past the halfway point, and what comes after the main sequence is a transformation so violent that it will reshape the entire inner solar system. On February 14th in 1990, NASA's Voyager 1 spacecraft was more than 3.7 billion miles from Earth, on its way out of the solar system after completing its primary mission of flying by Jupiter and Saturn. On the suggestion of astronomer Carl Sagan, the mission team commanded Voyager 1 to turn its camera around and take a final photograph of the solar system from the outside looking in. The result was a mosaic of 60 frames, and in one of those frames, at the request of a human who wanted to see where we came from, the Earth appeared as a single pixel, a mote of dust suspended in a sunbeam. Sagan described the photograph in 1994 in his book Pale Blue Dot, in words that have become among the most quoted in the history of science. He wrote that the photograph put our world in perspective, a lonely speck in the great enveloping cosmic dark. He wrote that all of human history, every king and peasant and conqueror, every moment of hope and suffering had played out on this mote of dust suspended in a sunbeam. And he wrote that there was nowhere else we could go to, not yet, and that perhaps the only planet known to harbour life was a small rocky world in an unremarkable corner of a galaxy that was itself an unremarkable island in a universe of at least 2 trillion such islands. Voyager 1 had travelled far enough from the Sun that the Sun, as seen from Voyager's camera position, was a brilliant star rather than the solar disk visible from Earth. The sunbeam in the photograph was not sunlight falling on the pale blue dot of Earth. It was an optical artifact, a diffraction spike created by the camera's optics when pointing close to the Sun. But the metaphor held. Earth was a mote of dust in the solar system, and the solar system was a mote of dust in the galaxy, and the galaxy was a mote of dust in the universe. No one expects that the pale blue dot photograph resolved any scientific questions. Its value was entirely philosophical. It demonstrated in a way that text and diagrams cannot what the solar system actually looks like from the scale of the outer planets. The Sun, from 3.7 billion miles, was still easily the brightest object in the photograph, still the centre of gravity around which everything in the solar system moves, but small, a point of light that you could cover with a grain of sand held at arm's length. Voyager 1 has continued outward since 1990. It crossed the termination shock of the solar wind in 2004 and entered the heliosheath. In 2012, it crossed the heliopause into interstellar space. As of 2026, Voyager 1 is roughly 160 astronomical units from the Sun, travelling away from the solar system at about 38,000 miles per hour. It is the most distant human-made object in existence, and it is carrying a golden record, a physical artifact intended as a message to any intelligent civilization that might encounter it in the vastness of interstellar space. The golden record contains greetings in 55 human languages, music from 27 countries, natural sounds from Earth, and 116 encoded images depicting Earth and life on it. The record was assembled under the supervision of Carl Sagan and includes pieces of music ranging from a Bach Brandenburg concerto to Chuck Berry's Johnny B. Good, sounds of surf and thunder and birdsong and human heartbeats, and greetings from then President Jimmy Carter. At Voyager 1's current speed, it will take roughly 40,000 years to come within 2 light years of any other star. It is not heading toward any particular star, and carries no propulsion. It is simply drifting. The probability that any civilization will ever find it is effectively zero unless interstellar space is far more populated with technological species than any evidence suggests. But the record is out there. The sun's light has already passed Voyager 1, left it behind years ago, and continues outward at its constant speed of 186,282 miles per second. The relationship between the Voyager spacecraft and the sun's light illustrates something important about the hierarchy of distances in the solar system. Voyager 1 has been travelling for nearly 50 years and is about 160 astronomical units from the Sun. A photon from the Sun crosses that distance in about 22 hours, not 50 years. Light is fast in a way that spacecraft with our current technology simply cannot match. The nearest star at 424 light years would take Voyager 1 approximately 73,000 years to reach at its current speed, but light makes the crossing in 4.24 years. No one predicts that humanity will reach the nearest star on any timescale shorter than many thousands of years with current technology. But the sun's light, already far ahead of anything we've ever built, is there right now, arriving at Proxima Centauri in 424 years, at Alpha Centauri A and B in 437 years, at Barnard's star in 596 years. The sun's light is humanity's fastest ambassador, already distributed across a sphere of space that makes our spacecraft look like they are barely moving. Before we get started on the question of dark energy and the ultimate limit on how far that light can go, it is worth keeping this in mind. The universe, as seen from the sun's perspective, is not a place that is impossibly distant and inaccessible. Light reaches it constantly. The sun has been sending photons into the universe for 4.6 billion years. Some of those photons have already travelled 4.6 billion light years from Earth, and they keep going. The sun, in terms of its electromagnetic influence, is an object with a reach we can barely comprehend. That reach has a limit, defined by dark energy, and tonight we're going to find out exactly where it is. The sun is not a uniform, steady light source. It varies. Its output changes on timescales from minutes to thousands of years, driven by processes in its interior and its magnetic field that we are still in the process of understanding. The most familiar variation is the 11-year sunspot cycle, a periodic rise and fall in the number of dark spots visible on the sun's surface that has been documented by observers since the early 17th century and studied systematically since the 19th. Sunspots are regions of the photosphere where intensely concentrated magnetic field lines emerge from the interior. The magnetic field is so strong in these regions that it inhibits the normal convective transport of heat from below, making the sunspot region several thousand degrees cooler than the surrounding photosphere. A temperature of roughly 6,300 degrees Fahrenheit instead of 10,000 degrees Fahrenheit may not sound dramatically different, but the intensity of thermal emission depends on the fourth power of the temperature, which means a sunspot emits only about a quarter of the light of the surrounding photosphere. This is why sunspots appear dark by contrast, even though they are still extremely hot by any terrestrial standard. If you could isolate a sunspot and look at it against the night sky, it would glow orange, bright, hotter than any flame on Earth. The 11-year cycle begins at solar minimum, when sunspot activity is at its lowest and the sun's surface is relatively quiet. Over the next 5 or 6 years, the cycle rises to solar maximum, with sunspots appearing in increasing numbers at lower and lower latitudes on the solar surface, in a pattern called Sporer's law. At solar maximum, the sun's magnetic poles undergo a reversal, with the north and south magnetic poles swapping positions. The magnetic configuration that created the previous cycle of sunspots is erased, and a new one begins to build, reversed in polarity. The cycle then declines over the next 5 or 6 years back to solar minimum, and the whole pattern repeats. The total solar irradiance, the amount of energy per unit area that the sun delivers at Earth's orbit, varies by roughly 0.1% over the course of the solar cycle, with the maximum occurring near solar maximum rather than solar minimum. This seems counterintuitive given that sunspots are darker than the surrounding photosphere, but sunspots are accompanied by bright facular regions, areas of enhanced emission surrounding the sunspots that more than compensate for the reduced output of the spots themselves. The net effect is a slight increase in total solar output near solar maximum. A 0.1% variation in solar output has detectable effects on Earth climate, but they are small compared to other climate drivers such as greenhouse gas concentrations and volcanic activity. No one expects the solar cycle to be responsible for more than a fraction of a degree of global temperature change from one solar minimum to the next solar maximum, but there are longer-term variations in solar activity that have historically correlated with significant climate shifts. The Maunder minimum was a period from approximately 1645 to 1715, when sunspot activity was almost entirely absent for several decades. The mechanism responsible for this prolonged quiet is not fully understood, but it appears to represent a state where the solar magnetic dynamo that drives sunspot activity weakened significantly. The Maunder minimum coincided with a period of lower temperatures in many parts of the world, particularly in Europe, during what is sometimes called the Little Ice Age, though the connection between the two is debated and other factors, including volcanic eruptions, contributed to the cooling. The Maunder minimum and similar extended quiet periods, including the Spora minimum from roughly 1460 to 1550, and the Wolf minimum from roughly 1280 to 1350, demonstrate that the 11-year sunspot cycle is not perfectly regular. The Sun has periods of enhanced activity and periods of extended quiet on timescales of decades to centuries. Current solar cycle 25, which began in December 2019, has been more active than predictions suggested, with sunspot counts exceeding the expected maximum in 2024. This is consistent with the Sun being a dynamic system rather than a simple, clockwork periodic oscillator. On longer timescales, the Sun's total energy output has been gradually increasing over its lifetime. A 4.6 billion year old star like the Sun is about 30% more luminous than it was at its birth. Early in the Sun's history, its lower luminosity meant that Earth received significantly less solar energy, raising what is called the faint young sun paradox. Geological evidence shows that the early Earth had liquid water and a relatively warm climate even when the Sun was much dimmer. The resolution of this paradox likely involves a much thicker early atmosphere with higher concentrations of greenhouse gases, primarily carbon dioxide, methane and water vapour, that compensated for the reduced solar output. By the end of tonight, the Sun's variability over its lifetime is not an afterthought to the story of its light. It is part of the story. The light that reaches us today is brighter than the light that reached the first life on Earth. The light that will reach the solar system in 5 billion years, when the Sun is a red giant, will be orders of magnitude more intense than anything the current biosphere has experienced. And the light that the white dwarf emits after that will be a pale, cooling echo of the engine that powered a planetary system for 10 billion years. The solar wind is the invisible tide that shapes the inner solar system. It is a continuous stream of charged particles, primarily electrons and protons, flowing outward from the Sun's corona at speeds ranging from about 250 miles per second in the slow solar wind to over 500 miles per second in the fast solar wind. The solar wind carries with it the Sun's magnetic field, stretched and dragged outward as the particles travel away from the Sun, creating a structure called the interplanetary magnetic field that extends throughout the heliosphere. The solar wind was not directly detected until 1962, when the Mariner 2 spacecraft measured it during its journey to Venus, but its existence had been inferred earlier by a number of independent observations. Comet tails were a clue. Every comet has two tails, a dust tail that curves gently behind the comet's direction of travel, and an ion tail that points directly away from the Sun regardless of which direction the comet is moving. The ion tail is created by the interaction of solar wind with the gases evaporating from the comet's surface, pushing the ions directly away from the Sun. The existence of ion tails implies a radial outflow from the Sun, and this was predicted theoretically by solar physicist Eugene Parker in 1958, who called the flow the solar wind in his seminal paper. Parker's prediction was initially met with skepticism, but was vindicated by the Mariner 2 observations 4 years later. The solar wind arrives at Earth's orbit travelling at between 250 and 500 miles per second, about 8 to 15 minutes after leaving the Sun. But Earth is not an undefended target. Earth has a magnetic field, generated by the circulation of liquid iron in the outer core, and this magnetic field deflects most of the solar wind particles before they can reach the atmosphere. The region of space dominated by Earth's magnetic field is called the magnetosphere, and it extends roughly 37,000 miles sunward and many hundreds of thousands of miles in the antisolar direction, in a long magnetotail. The magnetosphere is not a simple shield. The solar wind compresses the sunward side of the magnetosphere and stretches the antisolar side, creating a tear-drop-shaped region of space that acts as a magnetic bubble around the Earth. Where the solar wind meets the magnetosphere on the sunward side, the particles are suddenly decelerated from supersonic to subsonic speeds, creating a standing bow shock roughly 37,000 to 43,000 miles from Earth. The region between the bow shock and the magnetopause, the outer boundary of the magnetosphere, is called the magnetosheath, and it contains turbulent, compressed solar wind plasma. The magnetopause is the boundary where Earth's magnetic field pressure balances the dynamic pressure of the solar wind. Most solar wind particles bounce off the magnetopause, but not all of them. Where Earth's magnetic field lines connect with the interplanetary magnetic field at the poles, particles can stream directly into the upper atmosphere along the magnetic field lines, creating the aurora borealis and aurora australis. The aurora is visible light produced when energetic solar wind particles collide with oxygen and nitrogen atoms in the upper atmosphere, exciting them to higher energy states and causing them to emit light as they return to their ground state. The specific colours depend on the atom, the altitude, and the energy of the collision. Oxygen at high altitudes emits red, oxygen at lower altitudes emits the familiar greenish glow, and nitrogen emits blue and purple. During a geomagnetic storm, when a coronal mass ejection from the Sun arrives at Earth and compresses the magnetosphere, the auroras can extend to much lower latitudes than normal. During the Carrington event of 1859, auroras were seen as far south as the Caribbean. During the Halloween solar storms of 2003, auroras were visible in Texas and Florida. During a major geomagnetic storm in May 2024, auroras were visible across much of the continental United States and as far south as Mexico. Absolutely no one anticipates that the solar wind, despite its invisibility, is passive background. Its effect on Earth's space environment is constant and significant. It is responsible for the gradual sputtering of planetary atmospheres as energetic solar wind ions kick atmospheric molecules to escape velocity. Mars, which lost its magnetic field billions of years ago due to the cooling of its iron core, has been stripped of most of its atmosphere by the solar wind over the past 4 billion years, a process that NASA's MAVEN mission has been measuring directly since its arrival at Mars in 2014. The solar wind has effectively carved away the Martian atmosphere, leaving a thin remnant that is less than 1% as dense as Earth's atmosphere. Venus, despite having no significant magnetic field, has retained a thick atmosphere because its thick carbon dioxide atmosphere provides enough pressure and chemical complexity to resist solar wind stripping at the rates seen at Mars. The interaction of the solar wind with Venus creates a bow shock and an induced magnetosphere without any internal magnetic field, a structure quite different from Earth's, and researchers are still studying why Venus has been more successful at retaining its atmosphere than Mars. For the question of where the sun's light ultimately goes, the solar wind matters because it defines the boundaries within which the light first escapes. The light leaves the photosphere, passes through the corona that is heated by the same magnetic processes that drive the solar wind, and then travels outward through a magnetized plasma environment that extends all the way to the heliopause. The photons are not affected by the magnetic field of the solar wind, but they are travelling through a medium that is energized and structured by the same processes that produce the solar wind. The sun is not just a source of light, it is a system, and the light is one output of a much more complex engine. The light from the sun is not simply bright white, it contains information. Encoded in the spectrum of solar light, in the precise distribution of wavelengths from ultraviolet through visible to infrared, is a detailed record of the sun's composition, temperature, magnetic field, and surface dynamics. Reading that spectrum is one of the most productive acts in the history of science, and the technique that makes it possible, spectroscopy, is also the primary tool by which we understand the composition and evolution of every other star in the universe. When sunlight passes through a prism or diffraction grating and is spread into its component wavelengths, it does not produce a smooth, continuous rainbow. It produces a rainbow crossed by hundreds of dark lines, each at a precise wavelength. These dark lines, called Fraunhofer lines, after the German physicist Joseph von Fraunhofer, who catalogued them systematically in the early 19th century, are the shadows of specific atoms and ions in the sun's atmosphere. When light from the sun's hot interior passes through the cooler gas of the photosphere and chromosphere, atoms in those layers absorb photons at precisely the wavelengths corresponding to their electron energy transitions and emit them in random directions. The result is a deficit of photons at those specific wavelengths in the light that eventually reaches Earth. By identifying the wavelengths of the dark lines in the solar spectrum and matching them to known absorption lines of specific elements measured in the laboratory, astronomers can determine which elements are present in the sun's atmosphere and in what proportions. This technique, applied to the sun and then extended to other stars, established the chemical composition of stellar atmospheres throughout the universe. It revealed that the sun is composed primarily of hydrogen and helium, with smaller amounts of oxygen, carbon, nitrogen, silicon, magnesium, sulfur, and essentially every other element in the periodic table present in trace amounts. No one predicts the solar spectrum is static. It varies with the solar cycle, with sunspot activity, and with the specific dynamics of the photosphere at any given moment. The dark lines shift slightly in wavelength due to the Doppler effect as different parts of the solar surface move toward or away from us due to convection and rotation. The sun's equator rotates faster than its poles, roughly 25 days at the equator versus 35 days near the poles, a phenomenon called differential rotation, and this rotation produces a measurable Doppler shift in the spectral lines from opposite edges of the solar disk. The Doppler shift is also the key technique by which we detect exoplanets and measure the composition and velocity of distant objects. When a planet orbits a star, it causes the star to wobble slightly, which produces a periodic Doppler shift in the star's spectral lines. This technique, called radial velocity or Doppler spectroscopy, was the method used to detect the first confirmed exoplanet around a sun, like Star in 1995 by Michel Mayor and Didier Queloz, work for which they received the Nobel Prize in Physics in 2019. The technique they used on 51 Pegasi was exactly the same technique Fraunhofer and Kirchhoff applied to the Sun nearly 2 centuries earlier. The infrared spectrum of the Sun is particularly important for the question of the Sun's energy output, because the infrared contains a large fraction of the Sun's total energy. When sunlight strikes Earth's surface, it delivers energy across a broad spectrum, and different parts of the spectrum interact differently with Earth's atmosphere and surface. Visible light penetrates the atmosphere efficiently and warms the surface. Infrared radiation is partially absorbed by water vapour and carbon dioxide in the atmosphere. ultraviolet radiation is partially blocked by the ozone layer. The balance of these interactions determines Earth's energy budget and climate. The ultraviolet component of sunlight, despite being only a few % of the total solar output, is of critical biological importance. UV, B radiation from the sun, in the wavelength range from 280 to 315 nanometers, is energetic enough to damage DNA by causing thymine dimers, lesions where adjacent thymine bases in the DNA double helix become abnormally joined. This is the mechanism by which excessive UV exposure causes sunburn and eventually skin cancer. The ozone layer in Earth's stratosphere absorbs most UV, B before it reaches the surface. Without the ozone layer, UVB levels at Earth's surface would be orders of magnitude higher and would make the surface far more hostile to life. Before we get started on the final section of tonight's story, the solar spectrum encodes one more piece of information worth mentioning. Because the expansion of the universe stretches photon wavelengths to longer values, the light we receive from distant galaxies is red-shifted. The spectral lines appear at longer wavelengths than they would in a laboratory. The degree of redshift tells us how much the universe has expanded since that light was emitted, and this is how we measure the distances to galaxies and the structure of the universe. The same spectral lines that Fraunhofer identified in sunlight in the early 19th century are present in the light of every star in every galaxy we can observe, shifted by the expansion of space from the wavelengths Fraunhofer catalogued. The sun's spectrum is the reference standard for understanding the composition and motion of the entire observable universe. In approximately 5 billion years, the nuclear reaction at the centre of the sun will begin to falter in a specific and predictable way. The sun has been fusing hydrogen into helium in its core since it formed from a collapsing cloud of gas 4.6 billion years ago. The hydrogen in the core is not unlimited. Over billions of years, the proportion of helium has been rising as hydrogen is consumed, and the proportion of fresh hydrogen available for fusion has been falling. When the hydrogen in the core is depleted below a critical threshold, the nuclear reaction will lose the energy output needed to support the mass of the star pressing down on it from above. What happens next is one of the most dramatic transformation sequences in stellar physics, and it will unfold on a timescale of billions of years, but also, in cosmic terms, with a kind of inevitability that makes it feel like the ticking of a very slow clock. The core of the sun will begin to contract under gravity, because it is no longer generating enough pressure to support itself. As it contracts, it heats up. The heat from the contracting core is transferred to a shell of hydrogen just outside the core, which is still available for fusion. This shell ignites, beginning to burn hydrogen in a ring around the now dead helium core. The energy output from this shell burning hydrogen is greater than the energy output from the original core burning, and this excess energy forces the outer layers of the sun to expand. They expand dramatically. Over tens of millions of years, the sun will swell from its current diameter of roughly 865,000 miles to perhaps 100 to 200 times that size, becoming what astronomers call a red giant. The surface temperature will drop as the surface spreads over a much larger area, cooling from the current roughly 10,000 degrees Fahrenheit to perhaps 4,000 to 5,000 degrees Fahrenheit. The colour will shift from the current white, yellow, to orange, red. The luminosity will not drop with the surface temperature, however, because the surface area has increased so enormously. The total energy output of the red giant sun will be roughly 1,000 to 2,000 times greater than the current sun. This is the first of tonight's counterintuitive reversals. The sun will become simultaneously cooler on its surface and vastly brighter as a whole. The energy it delivers to the inner solar system will increase to levels that are catastrophic for any life remaining on the inner planets. The sequence of destruction for the inner planets begins early in the red giant phase, when the sun's expanding outer envelope begins to engulf them. Mercury will be the first to go, consumed by the expanding solar atmosphere millions of years before the maximum expansion is reached. Venus will follow. The fate of Earth is debated among solar physicists. Some models suggest that the outer boundary of the red giant sun will extend just past Earth's current orbit. Other models suggest Earth will just barely survive the maximum expansion. But even if Earth escapes being physically swallowed, the fate of its surface is not in question. The increased luminosity will boil away the oceans within roughly 1 billion years of the onset of the red giant phase, long before the maximum expansion is reached. The runaway greenhouse effect will strip the atmosphere. The surface temperature will rise to levels at which rock volatilizes. No one predicts a comfortable future for the inner solar system in the red giant phase. But it is worth noting what the red giant phase will mean for the rest of the solar system. The outer planets, currently too cold to sustain liquid water on their surfaces, will experience a dramatic warming. Jupiter, at 5 astronomical units, will receive energy inputs comparable to what Earth receives today. Saturn, Uranus, and Neptune will shift into warmer ranges. The moons of the outer solar system, currently ice, covered worlds with subsurface oceans maintained only by tidal heating, will see their icy surfaces melt and become true liquid water oceans for the first time. For perhaps 1 billion years during the red giant phase, the outer solar system will experience the closest analogue to Earth-like conditions it has ever had or will ever have. This is not a comfortable fact. It does not help the life that exists on Earth now, which will be gone long before the red giant phase peaks. But it is a remarkable feature of the Sun's evolution that the habitable zone of the solar system will migrate outward over time, and that for a limited window of geological history the moons of Jupiter and Saturn will sit in what was once a deep freeze. The red giant phase is not stable, however. While the outer layers are expanding and cooling, the helium core is continuing to contract and heat. When the core temperature reaches approximately 180 million degrees Fahrenheit, a new nuclear reaction ignites, helium fusion. Helium nuclei begin fusing into carbon and oxygen in a reaction called the triple alpha process. The onset of helium fusion in a red giant star is not gradual. It happens all at once in an event called the helium flash, an explosive ignition of the helium core that releases in a matter of seconds more energy than the Sun currently produces in a year. No one expects to be around to observe the helium flash of our Sun, but astronomers have studied it in other stars. The helium flash does not blow the star apart. The energy is absorbed by the outer layers and dissipated. But it does cause the star to reorganize dramatically. The core expands as helium burning begins in earnest, and the outer layers contract somewhat in response. The star settles into a new, more stable configuration called the horizontal branch, burning helium in its core and hydrogen in a shell around the core simultaneously. It becomes somewhat smaller and hotter than it was at its red giant peak, and it remains in this configuration for roughly 100 million years. After the helium in the core is exhausted, the star goes through a second red giant phase, called the asymptotic giant branch, which is even larger and more luminous than the first. The outer layers of the star become increasingly unstable, pulsating and throwing off material in strong stellar winds. The Sun, in this phase, will shed perhaps 1/4 to half of its total mass into space in the form of gas and dust, expanding into a slowly expanding shell of material surrounding the shrinking stellar core. This expanding shell is what we see when we observe other dying stars of similar mass in the galaxy. They are called planetary nebulae, not because they have anything to do with planets, but because they appeared planet, like in early telescopes with their round, glowing shapes. The planetary nebula phase is one of the most visually spectacular phenomena in astronomy. The Helix Nebula, sometimes called the Eye of God, is a planetary nebula about 650 light years from Earth, and it is what our Sun will look like in roughly 6 billion years, seen from a distance of several hundred light years. A glowing shell of expelled gas, illuminated by the intensely hot stellar remnant at its centre, expanding at roughly 25 miles per second into the surrounding interstellar medium. The Helix Nebula is approximately 2.5 light years across, and it is still expanding. The shell of gas it represents was expelled over the last few tens of thousands of years of the asymptotic giant branch phase of its progenitor star, and the ultraviolet radiation from the hot white dwarf at its centre is ionizing the gas, making it glow. In roughly 10,000 years, the shell will have expanded enough that the white dwarf's radiation can no longer effectively ionize it, and the nebula will fade. The gas will disperse into the interstellar medium, enriched with carbon and oxygen and other elements synthesized in the star's interior, available to be incorporated into the next generation of stars and planets. This is how the galaxy recycles its material. This is how the carbon in every living thing on Earth was made. By the end of tonight, the sun's death is not just the death of a star, it is the creation of new raw material. The outer layers of the sun, blown off in the asymptotic giant branch winds and in the planetary nebula, will eventually seed a new star, forming regions with the elements that the sun spent 10 billion years manufacturing. In a very real sense, the sun is cooking the ingredients for future solar systems right now, and its death will be the moment those ingredients are returned to the galactic kitchen. The fate that awaits our sun, the red giant phase, the planetary nebula, the white dwarf, is not a guess or a computer model. It is an observation. We can look at stars at different stages of their evolution in the galaxy today and see directly what stars like our sun look like at each phase of their life cycle. The galaxy is a library of stellar life stages, with every chapter in the story illustrated by a real star we can observe right now. The star Arcturus, visible as a bright orange, red star in the spring sky in the northern hemisphere, is a red giant that gives us a preview of what our sun will look like in roughly 5 billion years. Arcturus is roughly the same mass as the sun but older, further along its evolutionary track and already in the red giant phase. Its surface temperature is about 7,300 degrees Fahrenheit, considerably cooler than our sun's roughly 10,000 degrees, and its diameter is about 25 times that of our sun. Its luminosity is about 170 times that of our sun. If Arcturus replaced our sun, its surface would extend to roughly half the distance from the sun to Mercury. From Earth, it would fill a significant portion of the sky and would deliver so much energy that Earth's surface temperature would rise far above any value compatible with liquid water. The star Betelgeuse, the bright red-orange star marking the shoulder of the constellation Orion, is an example of a much more massive star in the red supergiant phase, the equivalent of the red giant phase for stars that are 10 to 25 times the mass of the Sun. Betelgeuse is between 700 and 1,000 light years from Earth, and is one of the most intrinsically luminous stars in the local galaxy, with a diameter perhaps 700 to 1,000 times that of our Sun. If Betelgeuse were placed at the centre of our solar system, its surface would extend past the orbit of Mars, possibly past the orbit of Jupiter. No one predicts Betelgeuse will evolve like our Sun. It is far too massive. It will eventually undergo core collapse and produce a supernova, leaving behind a neutron star or black hole rather than a white dwarf. But observing Betelgeuse gives us a dramatic illustration of how large red giant and supergiant stars can become. The Helix Nebula, located about 650 light years from Earth in the constellation Aquarius, is a planetary nebula in the same class as what our Sun will produce. It is one of the largest and nearest planetary nebulae to Earth, which is why it appears so large in the sky, roughly half the angular diameter of the full moon. The white dwarf at its centre has a surface temperature of roughly 200,000 degrees Fahrenheit, much hotter than our Sun's surface today, because it has only recently been exposed by the loss of the outer stellar layers. It is emitting intense ultraviolet radiation that is ionizing the expanding shell of gas, making it glow in the characteristic colours of ionized oxygen and hydrogen that make planetary nebulae so visually striking. The shell of gas in the Helix Nebula is expanding at roughly 25 miles per second and has a radius of roughly 1.3 light Years. The white dwarf at the centre of the Helix Nebula will cool and dim over billions of years, just as our Sun's white dwarf will. The shell of gas will expand and thin and eventually become undetectable against the background interstellar medium. The white dwarf will be left alone, a dense, cooling cinder of carbon and oxygen, gradually fading toward the dark. Sirius B, the white dwarf companion to the brightest star in the night sky, is a useful example of a white dwarf in a less extreme state. Sirius B is roughly 8.6 light years from Earth, making it one of the nearest white dwarfs, and it is roughly the mass of our Sun compressed into a sphere about 1.2 times the diameter of Earth. Its surface temperature is currently around 45,000 degrees Fahrenheit, still hot but considerably cooler than a newly formed white dwarf. It was discovered in 1862 by astronomer Alvan Graham Clark, using the largest refracting telescope of the time, and its existence had been predicted earlier from the gravitational wobble it induces in Sirius A's motion. Sirius B is estimated to be roughly 100 million to 230 million years old as a white dwarf, and its cooling curve is consistent with the theoretical models. It is a point in our future, the Sun in a few billion years from now, after it has passed through its red giant phase and its outer layers have dispersed. A white dwarf about the mass of the Sun, warm and slowly cooling, in orbit with or alone in a solar system that has been radically transformed by the star's death. The Ring Nebula in the constellation Lyra is another nearby planetary nebula, about 2,000 light years from Earth. Its white dwarf central star is extremely hot, with a surface temperature over 200,000 degrees Fahrenheit, and is actively ionizing the surrounding ring of gas. The ring appears elliptical when viewed from Earth, but is actually a barrel-shaped structure of gas that we are viewing nearly end-on. The Hubble Space Telescope has imaged the Ring Nebula in extraordinary detail, revealing a complex inner structure of ionized knots and filaments within the expanding shell. The JWST observed it in 2023 and revealed even finer detail, showing the clumpy, irregular texture of the expanding gas and the magnetic field structure that influences how the gas flows outward from the white dwarf. By the end of tonight, the fact that we can observe stars at every stage of the life cycle our Sun will follow is not just a scientific convenience. It is a demonstration that stellar evolution is not a theory, but a history of the galaxy, written in the light of stars at every age and phase. The Sun's story is not unique. Billions of stars have already passed through the phases that lie ahead for our Sun, and the evidence of their passage is scattered across the galaxy in the form of white dwarfs, planetary nebulae, and the enriched interstellar medium from which new stars are forming right now. Our Sun's death, 5 billion years from now, will be one more chapter added to a story that has been unfolding for the entire history of the galaxy. The faint young sun paradox is one of the most interesting puzzles in the entire history of the solar system, and it bears directly on the story of the Sun's light over geological time. The paradox is this. Based on stellar physics, we know that the Sun was about 70% as luminous when it formed 4.6 billion years ago as it is today. The Sun's luminosity has been increasing steadily as hydrogen in its core is converted to helium and the core slowly contracts and heats. A 30% reduction in solar luminosity by straightforward atmospheric models should have kept Earth's surface temperature permanently below the freezing point of water throughout the first 2 to 3 billion years of Earth's history. But geological evidence tells a different story. The oldest rocks on Earth, dating to roughly 4 billion years ago, show clear signs of liquid water activity. Ancient zircon crystals from Australia dating to 4.4 billion years ago suggest the presence of liquid water at the surface. The ancient geological record of Mars, which is even older, shows river valleys, lake beds, and deltas that required liquid water flowing on the surface. The early Earth was not a frozen snowball. It was a warm, wet world with active oceans and weather. The reconciliation of the faint young sun with the evidence for warm early Earth requires the early atmosphere to have been dramatically richer in greenhouse gases than the current atmosphere. Carbon dioxide is the most likely candidate. In the early Earth, volcanic activity was more intense than today due to the planet's higher interior heat, and the carbon, silicate cycle that draws down atmospheric carbon dioxide by weathering rocks had not yet evolved to its current efficiency. High concentrations of carbon dioxide, perhaps 100 to 1,000 times the current atmospheric concentration, would have been sufficient to maintain liquid water temperatures even with a dimmer sun. Methane may have played a role as well. Before the Great Oxidation Event roughly 2.4 billion years ago, Earth's atmosphere was essentially free of oxygen, and the microorganisms that dominated early Earth included methane, producing archaea. Methane is a more potent greenhouse gas than carbon dioxide per molecule, and significant atmospheric methane concentrations, perhaps in the range of 100 to 1,000 parts per million compared to today's roughly 2 parts per million, would have contributed substantially to warming. No one expects the faint young sun paradox to have a single simple resolution. The current scientific consensus is that a combination of factors, higher carbon dioxide, atmospheric methane, perhaps slightly different albedo of the early Earth without large continental masses, and possibly even tidal heating from a closer and larger early moon, all contributed to maintaining liquid water conditions. Different epochs of Earth's early history may have been warmer or cooler depending on which factors dominated, and evidence suggests there were at least 2 global glaciation events, sometimes called snowball Earth events, around 2.4 billion years ago, and again around 700 million years ago, when ice extended to tropical latitudes and feedback mechanisms were just barely strong enough to prevent permanent glaciation. The faint young sun paradox also has implications for the search for life on other planets. If the Earth could maintain liquid water conditions under a significantly dimmer sun through greenhouse warming, then the habitable zone around a star, the range of orbital distances where liquid water can exist on the surface, is not a fixed ring. It is a dynamic region that depends on the atmospheric composition of the planet, the age of the star, and feedback processes involving geological and biological activity. A planet that might appear to be in the cold zone of its star today might have been habitable in the past under different atmospheric conditions, or might become habitable in the future as the star brightens. Absolutely no one anticipates that the habitable zone concept is simple or static. Planetary habitability is a function of the star, the planet's atmosphere, the planet's geology, and the planet's history. The faint young sun paradox reminds us that our own planet was habitable under conditions quite different from today's, and that the sun's evolving luminosity has been a constant background to the entire history of life on Earth. The algae that produced Earth's first oxygen 2.4 billion years ago were doing so under a sun that was several percent dimmer than it is now. The dinosaurs lived under a sun that was perhaps 1% brighter than the primordial sun. We live under the brightest sun Earth has ever had, and the sun of 5 billion years from now, on its way to becoming a red giant, will be the brightest it has ever been before its transformation. The sunlight falling on Earth today is one snapshot of a light source that has been changing for 4.6 billion years and will continue to change for another 5 billion years. The sun's light that reaches us tonight is brighter than any light that fell on any of our ancestors going back to the beginning of life on Earth, and every generation that comes after us will live under a slightly brighter sun, until finally the sun becomes something else entirely. When the planetary nebula disperses and the stellar winds subside, what remains of the sun is a white dwarf. It is the compressed remnant of the solar core, the object that will be the final physical form of our star for the remainder of cosmic time. Understanding what a white dwarf is, what it does, and how long it lasts is essential to understanding where the last light of the sun will go, because the white dwarf will still be emitting light long after every planet, moon, and asteroid in the solar system has been either consumed, ejected, or destroyed. A white dwarf is not a burning star in the conventional sense. It is not fusing hydrogen or helium or any other element in its core. There is no nuclear reaction sustaining it against gravity. Instead, it is supported against gravitational collapse by a quantum mechanical effect called electron degeneracy pressure. In ordinary matter, electrons can be squeezed only so close before the Pauli exclusion principle, a fundamental rule of quantum mechanics, forbids them from occupying the same quantum state. This quantum pressure can support a stellar remnant against gravity without any energy source, indefinitely, as long as the remnant's mass stays below a critical limit called the Chandrasekhar limit, roughly 1.4 times the mass of the Sun. The white dwarf that our Sun produces will be approximately 0.5 to 0.6 times the mass of the current Sun, compressed into a sphere roughly the size of Earth. The density will be approximately 1,000,000 times that of water. A teaspoon of white dwarf material would weigh several tons. The gravity at the surface will be roughly 100,000 times the gravity at Earth's surface, strong enough that any ordinary matter that falls onto the white dwarf is compressed and heated instantly upon impact. When the white dwarf first forms, it is extraordinarily hot. The core of the asymptotic giant branch star, exposed by the loss of the outer layers, can have temperatures in the range of 180,000 to 250,000 degrees Fahrenheit at its surface. No longer burning fuel, it is simply a hot ball of carbon and oxygen wrapped in a thin layer of hydrogen and helium, radiating energy into space through thermal emission. It glows white, with its peak emission in the ultraviolet and the blue end of the visible spectrum. Over time, it will cool. The cooling of a white dwarf is slow. Without an internal energy source, it can only lose the thermal energy it has stored, and the rate at which it cools depends on its surface area and temperature. The Stefan-Boltzmann law tells us that the energy radiated per second by a hot body depends on the fourth power of its temperature and the first power of its surface area. A white dwarf has a small surface area compared to its total energy content. It cools quickly at first, when it is very hot, then more and more slowly as it cools and the radiation rate drops. Astronomical models suggest that a white dwarf cools from its initial temperature of several 100,000 degrees to around 10,000 degrees Fahrenheit, roughly the current surface temperature of our Sun, over a period of billions of years. The cooling rate then continues to slow. Over tens of billions of years, the white dwarf will pass through the colour range from white to yellow to orange to red as its temperature drops. At some point in the far future, perhaps 100 billion to several trillion years from now, the white dwarf will cool enough that it is no longer emitting visible light at all, becoming a dark, cold object called a black dwarf, effectively invisible except for its gravitational influence on surrounding space. No one expects a black dwarf to exist in the current universe. The universe is only about 13.8 billion years old, and the cooling time for a white dwarf to become a black dwarf is longer than the current age of the universe. There are no black dwarfs anywhere in the observable universe yet. The universe is still young enough that every white dwarf that has ever formed is still warm enough to glow. This is important for the question of the Sun's last light. The white dwarf that our Sun becomes will still be glowing billions of years from now, emitting a cooling stream of photons into an increasingly empty universe. The light it produces will not be the focused, energetic sunlight of the main sequence phase. It will be the fading thermal glow of an object that has no more energy to produce and is simply radiating what it has left. But it will be light, and it will travel outward into whatever the universe looks like at that time, which is a very different place from the universe we inhabit now. The question of what the universe will look like when the Sun's white dwarf is cooling toward darkness is worth spending a moment on, because it shapes the final destination of the photons the white dwarf emits. The universe will be older, much colder, and dramatically less populated with stars. Star formation will have largely ceased, because the gas available in galaxies will have been consumed by previous generations of star formation. The night sky, if any observer existed to look at it, would show fewer and fainter galaxies, most of them dominated by aging red dwarfs and the remnants of more massive stars. ordinary Sun-like stars will be rare, most of them having already passed through their red giant and white dwarf phases. The cosmos will be entering what cosmologists call the degenerate era, an epoch when the dominant luminous objects are white dwarfs, neutron stars, and the slow, burning red dwarfs that can sustain hydrogen fusion for hundreds of billions to trillions of years. No one predicts the exact brightness of the solar white dwarf at any specific future time, but astronomers can model it with reasonable confidence. At 1 billion years after formation, the white dwarf will still be quite bright, perhaps comparable to an A-type main sequence star in absolute luminosity. At 10 billion years after formation, it will have cooled to roughly the temperature of the current Sun, yellowish, white, still emitting significant light. At 100 billion years, it will be a dim orange object. At 1 trillion years, it may be a deep red ember, barely visible. And the photons those embers produce will be travelling through a universe that is becoming increasingly hostile to their journey. Not hostile in a way that stops them, but hostile in a way that makes their eventual destination impossible to predict. The expansion of the universe, already accelerating today, will continue to accelerate indefinitely if dark energy remains constant. The galaxies that are not gravitationally bound to the local group, the cluster of galaxies that includes the Milky Way and Andromeda, will continue to recede. Over billions of years, the light from those receding galaxies will be shifted to longer and longer wavelengths by the expansion of space, eventually becoming microwave radiation, then radio waves, and finally slipping below any possible detection threshold. By the end of tonight, the white dwarf that our Sun becomes will be the last light source of what was once our solar system. It will glow for longer than the current age of the universe, and when its photons travel outward from that tiny cooling ember, they will be entering a universe that is darker, emptier, and more profoundly isolated than anything we can easily imagine from where we sit now, at the bright midpoint of the Sun's life. In approximately 4.5 billion years, roughly the same timescale on which the Sun will be entering its red giant phase, the Milky Way and the Andromeda Galaxy will begin to merge. This is not a speculative prediction. It is one of the most certain events in the future of our solar neighbourhood, because the trajectories of the Milky Way and Andromeda have been measured with sufficient precision that the outcome is beyond reasonable doubt. Andromeda is currently approaching the Milky Way at roughly 70 miles per second, and its transverse velocity has been measured with the Hubble Space Telescope and confirmed to be small enough that the collision is unavoidable. The merger of two large spiral galaxies is not an event that happens quickly. It unfolds over billions of years, involving multiple passes where the two galaxies fall toward each other, interpenetrate, separate, fall together again, and gradually come to rest in a merged configuration. Computer simulations of the Milky Way-Andromeda merger, which have been run by multiple groups with increasingly detailed initial conditions, suggest that the first close approach, when the two galactic disks begin to interact gravitationally, will occur roughly 4 to 4.5 billion years from now. The first passage will distort both galaxies severely, sending stars from the outer disks into long tidal tails that will extend hundreds of thousands of light years into space. Despite the violence of the event as described, the merger is not likely to have significant direct effects on individual stars or planetary systems within the Milky Way. This is because the distances between stars are so vast that even in the most densely populated regions of either galaxy, the probability of two stars actually colliding during the merger is extremely low. What will change is the orbital structure. Stars that are currently moving in orderly circular orbits in the Milky Way's disk will be scrambled into more elliptical, disordered orbits, as the gravitational field of the merged system takes on a more complex elliptical galaxy configuration. No one predicts that the Sun's solar system will be disrupted in any dramatic way by the merger itself. The odds that the Sun will pass close enough to another star during the merger to destabilize the solar system are estimated at roughly 1 in 1,000. The most significant effect of the merger on the solar system is more subtle, The probability that the solar system will be flung into a different region of the resulting galaxy is significant. Stars from the outer disk are particularly likely to be scattered to larger radii, and the Sun, currently at about 26,000 light years from the galactic centre, might find itself at a very different distance from the merged galaxy's centre after the collision. The merged galaxy, which astronomers have informally called Milkomeda or Milkdromeda, will be an elliptical galaxy. Elliptical galaxies do not have the organised spiral structure of the Milky Way or Andromeda. Instead, their stars orbit in a variety of planes and directions, giving the galaxy a smooth, roughly ellipsoidal shape. Star formation in elliptical galaxies is generally low because the gas that fuels star formation has largely been consumed or expelled. The Milkdromeda galaxy will be an aging population of stars, gradually cooling and dimming over billions of years. No one expects the night sky as seen from a planet in the solar system to look the same through this period of the merger. Currently, our night sky shows the Milky Way as a band of light across the sky because we are embedded within a disk galaxy. As the merger begins, the night sky will be dramatically brighter, with the Andromeda galaxy growing from its current fuzzy ellipse, visible to the naked eye at the site of the Andromeda constellation, into a much larger and brighter structure filling an increasing portion of the sky. During the merger, the night sky may contain large, bright tidal structures and the bright cores of both galaxies visible simultaneously. When the merger is complete and the system has settled into an elliptical galaxy, the night sky will show a smooth haze of stars in all directions rather than a concentrated band. This is the environment in which the Sun will be completing its red giant phase. The red giant that the Sun becomes 5 billion years from now will be expanding in a galaxy that is in the process of merging with its neighbour. The white dwarf that follows will cool in the resulting elliptical galaxy, in a solar system that may be orbiting at a significantly different distance from the galactic centre than it does today, and in a sky that looks nothing like the one we see from Earth tonight. The Sun has already made about 20 orbits of the Milky Way since its formation. It will make perhaps another 20 before the merger begins. The solar system, after spending most of its life in a well-ordered spiral galaxy, will finish its story in a very different environment, orbiting the merged remnant of 2 galaxies in a universe that will look dramatically different from the universe of today. By the end of tonight, the merger with Andromeda is not separate from the story of the Sun's light and the Sun's death. It is the environment in which the Sun's final phase occurs. The white dwarf cooling toward darkness will be doing so inside a galaxy that does not look like the Milky Way at all, in a universe whose nearest visible neighbours will have changed significantly, in a sky that no human civilization alive today could recognise as familiar. The final photons of the solar white dwarf will be emitted into this transformed cosmos, and they will carry the Sun's last message outward into whatever the universe has become by then. Dark energy is one of the most profound things we do not understand about the universe. It was discovered in 1998, when 2 independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and another led by Brian Schmidt and Adam Rees at the HI Z Supernova Search Team, were using Type Ia supernovae to measure the expansion rate of the universe at different points in cosmic history. They expected to find that the expansion was slowing down because gravity should be pulling galaxies back together. Instead, they found that the expansion was speeding up. The discovery was so unexpected that both teams spent months checking their data, looking for systematic errors, before concluding that the result was real. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for the discovery. The name dark energy was coined for whatever is driving the acceleration, and it is a placeholder name for our ignorance. We know dark energy exists because of its gravitational effect on the expansion of the universe. We do not know what it is, where it comes from, whether it is constant over time, or whether it can be unified with any known field in physics. The most common interpretation of dark energy identifies it with the cosmological constant. a term that Einstein introduced into his general relativity equations in 1917 to allow for a static universe, then famously abandoned as his greatest blunder when Edwin Hubble's observations showed the universe was expanding. It turns out that a cosmological constant, a constant energy density of empty space, produces exactly the kind of accelerating expansion we observe. The value of the cosmological constant needed to match the observations is extraordinarily small, roughly 10 asteroids, 120 in natural units, which is one of the most extreme fine tuning puzzles in all of physics. The consequence of the accelerating expansion for the future of the universe is precisely what matters for the fate of the sun's last photons. If dark energy is constant, the expansion will continue to accelerate indefinitely. Over time, the observable universe, the region of space from which light has had time to reach us since the Big Bang, will not grow. It is currently about 46 billion light years in radius. But the region from which we could ever receive a future signal, the region within the cosmic event horizon, is shrinking. Galaxies that are currently within the cosmic event horizon are gradually receding toward it and eventually crossing it, after which no signal from them can ever reach us. The cosmic event horizon is currently about 16.5 billion light years from Earth. A photon emitted today by a galaxy exactly at the cosmic event horizon will never reach us. The expansion of space will carry the galaxy away faster than the photon can close the distance. A photon emitted today by a galaxy just inside the cosmic event horizon will, in principle, eventually reach us, but it will arrive incredibly redshifted and faint, having fought against the expansion of space for billions of years. For the sun's white dwarf, emitting photons in the far future of the universe, the situation is even more restricted. As the universe ages and dark energy continues to drive the expansion, the observable region accessible to any future observer will shrink. Galaxies that are currently within the local group will remain gravitationally bound and will eventually merge into a single massive galaxy over the next few billion years. But all galaxies beyond the local group will eventually recede beyond the event horizon and disappear from view. The last light from them will arrive, impossibly redshifted and faint, and then nothing more. By the time the sun's white dwarf has cooled to a dim red ember, trillions of years from now, the universe it is embedded in will be dramatically different from the universe of today. The only light sources visible to a hypothetical observer will be within the remnant local group galaxy, which will have merged into an elliptical galaxy containing the stars, white dwarfs, neutron stars, and black holes of the Milky Way, Andromeda, and the dozens of smaller galaxies in the local group. Beyond this merged galaxy, the universe will be effectively dark. The cosmic microwave background, the leftover thermal radiation from the Big Bang, will have been redshifted to wavelengths so long that no instrument could detect it. The other galaxies of the universe, the hundreds of billions of galaxies we can see today, will be invisible, having receded beyond the cosmic event horizon long ago. The photons that the cooling solar white dwarf emits in that era will travel outward into this dark, cold, isolated cosmos. Some of them, emitted in the direction of the merged local group galaxy, will circle endlessly through the gravitational field of the combined galaxy. Some will escape and travel into intergalactic space beyond the local group, heading toward a universe that has no visible galaxies in it, only empty expanding space and the dim remnants of whatever passed the event horizon before it closed. Those photons will travel for a very long time. No one predicts where the very last photon emitted by the solar white dwarf will go. The last photon, emitted just as the white dwarf finally cools to a temperature where no more thermal radiation is possible, will travel at 186,282 miles per second into an expanding universe. It will carry a tiny amount of energy and information about the object that emitted it. No receiver exists to detect it. No civilization, if any civilization remains anywhere in the universe at that time, could possibly know to look in the right direction at the right time. The photon will travel in a straight line, infinitely, unless it is absorbed by a particle of matter or falls into a gravitational singularity. In an empty, dark universe, neither of those fates is likely. Matter will have been consumed or dispersed. Black holes, the dominant remaining objects after all ordinary matter has decayed or been accreted, will themselves evaporate through Hawking radiation over timescales of 1067 to 10100 years, depending on their mass. Eventually, the universe will consist of nothing but Hawking radiation, a thin background of particles and photons with no organised structure at all. That last photon from the solar white dwarf will be out there somewhere in the far future. One photon among an expanding sea of thermal radiation, still travelling at the speed of light, still carrying information that a sun once existed in this corner of the universe. It is the final message, sent to no one, carrying the signature of a star that burned for 10 billion years and left nothing but a cooling cinder and, at the very end, a single departing photon. Tonight, we have followed the sun's light from its birth in the nuclear furnace of the core, through the millennia, long random walk through the solar interior, through 8 minutes of interplanetary travel to Earth, through the void of interstellar space, through the expanding universe to its current horizon. We have followed the sun itself through its remaining 5 billion years of hydrogen burning, into the red giant phase that will consume the inner solar system, through the planetary nebula, and into the white dwarf that will cool and dim and finally fall silent over trillions of years. And we have followed the last photon of that white dwarf into a universe that is dark and cold and expanding without destination. After the planetary nebula disperses and the white dwarf begins its long cooling arc toward darkness, the solar system's story continues for a surprisingly long time, even after the sun has effectively ceased to be a star. The white dwarf's gravitational field is unchanged from the sun's. It still has roughly half the sun's original mass concentrated in a sphere the size of Earth. The planets that survived the red giant phase, primarily the outer planets, will continue to orbit the white dwarf for billions of years, their orbital radii roughly unchanged because the reduction in mass during the stellar wind and planetary nebula phase is gradual enough that the orbits adjust adiabatically rather than catastrophically. Jupiter will survive the sun's red giant phase. Its orbital radius will actually increase slightly as the sun loses mass, because a less massive central body exerts less gravitational pull, allowing Jupiter to drift to a wider orbit. Saturn, Uranus and Neptune will similarly survive and drift outward. The Oort cloud objects, the trillions of icy bodies in the sun's outer gravitational well extending to perhaps 1 to 2 light years, will be partly disrupted by the sun's mass loss, but many will remain gravitationally bound in wider orbits. The white dwarf solar remnant will continue to exert tidal forces on the surviving planets, and over very long timescales, these tidal interactions and gravitational perturbations from passing stars will gradually destabilize planetary orbits. Monte Carlo simulations of planetary system evolution over multi-billion-year timescales suggest that the probability of a planet being ejected from the solar system by gravitational perturbations increases significantly over timescales of tens of billions of years. It is possible that one or more of the outer planets will be ejected from the solar system during the white dwarf phase, becoming free, floating rogue planets in interstellar space. No one predicts the exact sequence of events in the far future of the solar remnant with high confidence. The timescales involved are so long and the initial conditions so complex that different simulations give different outcomes. What is reasonably certain is that on timescales of hundreds of billions to trillions of years, the white dwarf solar remnant will gradually lose its planetary companions one by one, ending as an isolated, cold, dark object drifting through the galaxy. The physics of what happens to matter on very long timescales is an area of active theoretical research. Proton decay, if it occurs, would mean that on timescales of perhaps 1032 to 1036 years, the protons and neutrons that make up all ordinary matter would spontaneously transform into lighter particles. The white dwarf, composed of carbon and oxygen nuclei, would slowly dissolve into a soup of positrons and neutrinos on these timescales if proton decay occurs at the rates predicted by grand unified theories. However, proton decay has never been observed despite extensive searches, and the current experimental lower bound on the proton lifetime exceeds 10 of our 34 years for some decay modes. We do not know whether proton decay actually occurs. If proton decay does not occur, then the white dwarf's fate is determined by quantum mechanical tunneling processes on even longer timescales. At temperatures near absolute zero, quantum mechanics allows particles to tunnel through energy barriers that classical physics would forbid them from crossing. Over timescales of perhaps 10,000 years, the carbon and oxygen nuclei in the white dwarf could tunnel into iron, 56, the most stable nucleus, in a process of quantum cold fusion. The white dwarf would slowly crystallize into an iron sphere, releasing a tiny amount of energy in the process. Whether this actually occurs depends on the rate of quantum tunneling, which has never been measured at such low temperatures. The black holes that form from the most massive stars will persist longer than white dwarfs, if quantum effects cause ordinary matter to decay. A black hole loses mass through the emission of Hawking radiation, a quantum mechanical effect predicted by Stephen Hawking in 1974. The rate of Hawking radiation is inversely proportional to the mass of the black hole, so massive black holes radiate extremely slowly. A stellar mass black hole of perhaps 10 solar masses will take roughly 10^67 years to evaporate completely through Hawking radiation. Supermassive black holes like the one at the centre of the Milky Way, with a mass of roughly 4 million solar masses, will take roughly 1090 years. Eventually, every black hole in the universe will evaporate through Hawking radiation, leaving nothing but a burst of high-energy particles and a flash of thermal radiation. Absolutely no one anticipates that these timescales are easy to comprehend. The current age of the universe is roughly 13.8 billion years, which is 1.38 times 10^10 years. The timescale for a stellar mass black hole to evaporate through Hawking radiation, 10^67 years, is a number with 67 zeros. It is so much longer than the current age of the universe that any analogy fails. The best we can say is that compared to those timescales, the current age of the universe is essentially the first instant after the Big Bang. The universe at the end of the Hawking radiation era will contain nothing but extremely low energy photons, a thin gas of electrons and positrons, and perhaps a few other very light particles, all expanding apart from each other at the speed limit of the universe's dark energy-driven expansion. This is the true final state of the cosmos, sometimes called the heat death or maximum entropy state, a universe of such low energy density and such high entropy that no further work can be extracted from any energy gradient, and no further structure can form, no stars, no planets, no life, only the faintest possible background of radiation, expanding forever into a cold, dark and empty universe. The last photon from the solar white dwarf will be one participant in that ultimate background, diluted beyond any imaginable detection, carrying information about the sun in a cosmos where there is no one to receive it. Tonight, we followed the sun's light. We started in the nuclear furnace of the solar core, where hydrogen nuclei fuse under temperatures of 27 million degrees Fahrenheit, and where a photon of energy begins a journey that will take somewhere between 10,000 and 170,000 years just to escape the solar interior, bouncing endlessly through the dense plasma of the radiative zone, one random emission at a time. We follow that energy through the convective zone, where hot columns of plasma carry it upward to the photosphere. We watched it escape the chromosphere and the corona, where the magnetic field heats the outer atmosphere to temperatures millions of degrees hotter than the surface itself, a mystery that solar physicists are only now beginning to solve with instruments like the Parker Solar Probe flying inside the corona directly. We followed the photon outward at 186,282 miles per second through the solar system, past Mercury and Venus, past the pale blue dot of Earth in 8 minutes and 20 seconds, past Jupiter and Saturn and Neptune, out through the heliosphere, past the termination shock at 94 astronomical units, where the solar wind abruptly slows, across the heliopause at 122 astronomical units, where Voyager 1 crossed into interstellar space in 2012, and into the void between stars, where the photon travels in a straight line, uninterrupted, for the first time in its entire existence. We talked about what happens when that light arrives at the cosmic event horizon, the distance from us beyond which the expansion of space outpaces the ability of light to cross it. The event horizon today is roughly 16.5 billion light years away. A photon heading toward a galaxy beyond that boundary will travel for trillions of years and never arrive, because the space ahead of it expands faster than it can close the gap. There is a hard edge to how far the sun's light can go, and it is written into the physics of dark energy and the accelerating expansion of the universe. We followed the sun's future 5 billion years from now, when the hydrogen in the core runs out and the sun begins to transform. The outer layers will expand slowly at first and then dramatically until the sun is 100 to 200 times its current diameter, a red giant that will engulf Mercury and Venus and possibly Earth. The luminosity will rise to 1,000 to 2,000 times its current value, boiling away the oceans, stripping the atmosphere, turning the inner solar system into a zone of annihilation. The outer planets, and the moons that are too cold for life now, will for a brief window receive the warmth that Earth has always had. After the red giant phase, the outer layers of the sun will be expelled in stellar winds and a slow planetary nebula, a glowing shell of gas expanding outward, lit by the intense ultraviolet radiation of the exposed solar core. That core will be a white dwarf, roughly half the current mass of the sun compressed into a sphere the size of Earth, supported against gravity by electron degeneracy pressure, no longer fusing any fuel, simply radiating the heat it accumulated over 10 billion years of stellar life. The white dwarf will cool for billions, then trillions of years. It will shift from white to yellow to orange to red as its temperature falls. Eventually, far beyond the current age of the universe, it will cool to the point where it emits no visible light at all, becoming a black dwarf, invisible against the cold, dark, empty universe that will surround it by then. The last photon from the solar white dwarf will depart into a universe that is profoundly different from anything we can see tonight. The other galaxies will have receded beyond the cosmic event horizon, invisible, their light impossibly redshifted. The merged remnant of the Milky Way and Andromeda, the elliptical galaxy called Milkdromeda, will be the only significant structure visible. Even within it, star formation will have largely ceased, and the sky will be a quiet population of aging red dwarfs, white dwarfs, neutron stars, and the black holes that formed from the deaths of the most massive stars. That last photon will travel outward from the cooling white dwarf into this dark, cold cosmos. It will carry the final electromagnetic message of the sun, information about a star that burned for 10 billion years, that lit the evolution of the most complex life forms in its solar system, that produced every sunrise and sunset and reflected moonbeam and ocean sparkle and solar sail dream in the history of a species that looked up at the sky and wondered what lay beyond. The final place the sun will ever send its light is not a place you can point to on a map. It is wherever that last photon is, travelling at 186,282 miles per second into an expanding, dark and cooling universe, still moving, still carrying its message, in a cosmos that has almost entirely forgotten that any of this ever happened. Sleep well tonight. The sun will rise again in a few hours, right on schedule, as it has every day for 4.6 billion years. For now, let that be enough. Good night,